Hey, welcome to our next notes, series and the nth term test for divergence. So I'm going to let you read all that. That's pretty self-explanatory, I think. If you have any questions on it, you can ask me in class. So let's look at what we're doing here. So this says find the first four terms. So that would be a sub 1. If we plug a 1 in there, it's going to be 1. And a sub 2 is going to be 1/4. A sub 3 is going to be 1/8. Wait a second. 3/9, 1/9. I was thinking 2 cubed. 3 squared. 3 squared. Pay attention to the details. Plug a 4 in there. 1/16. Okay. Now the fourth partial sum would be what we get when we add those 4 up. So if we add those 4 up, probably what I would do is get a common denominator between these two. So that would be 4/4, so that's 5/16. And then if we do the ninths, that's 9/9, so that's 10/9, like that. And then the common denominator is going to be 1/44. So that's going to be 45 and 1/60, which is 205. So the fourth partial sum is 205 over 144. Okay, so that's pretty basic. So I don't really want to write this out. Every term is going to be a 2. It's a constant, so it's going to be 2. A sub 1 is 2, I guess. I want to write that up. A sub 1 equals A sub 2 equals A sub 3 equals A sub 4 equals 2. Okay. I guess technically we could box this as well because that was part of the question. Do this and this. But okay, so that's just 4 2's. So technically we should have 2 plus 2 plus 2 plus 2. Addition, multiplication is repeated addition. So that's going to be 8. All right, pretty basic stuff here so far. I guess we'll go ahead and do these. So the first term, that's going to be a -1, and that is going to be positive. That's going to be a 1/2, and that's going to be a -1/3, and that's going to be a 1/4. So again, I'm going to add these two together. So that's going to be 2/4. So that's going to be 3/4. And then here, that's 3/3. So that's going to be -4/3. So that's going to be 9/12 minus 16/12. So that's going to be -7/12 for the fourth partial sum. All right. Okay, so geometric series is when we multiply by the same number, a common ratio, over and over and over again. Usually call that a common ratio, the places I've seen it, but so notice that this summation starts at 0. Summations can start at different numbers. Thinking about changing one of these for next year. You don't highlight this, that's just for me. So just to show that it can start at a different number, I'm going to do that. Now, even if that was starting at 3 and we were finding the first 4 terms, the partial sum would still be 4 of the 4 terms that we found. So even if this started as a 3, in this example, that would still be a 4. Okay. Now, when I taught regular Algebra 2 back in the day, we taught this formula. So this is the formula for an infinite geometric sequence. If the common ratio is between 0 and 1, then the series is going to converge towards a value. And we could find the sum using this formula. So that should be a sub 1, really. if the absolute value of r is greater than 1 or equal to 1, then the series is going to diverge. Okay, in a geometric series, we can actually find the sum instead of just talking about that. So, when we look at this, hopefully we can kind of see a pattern here. So it looks like we're multiplying the numerator by 3 and maybe the denominator by 4. So it looks like we're probably multiplying by 3/4. So to figure that out, if you think it's geometric, what you can do is you can take a term and divide it by the term before it. Because if you have a common ratio, that's what it's going to be. So if we take 3/2 divided by 2, that's a complex fraction. So I'm going to multiply by 2/2, and that's going to give us 3/4. So r equals 3/4. We're multiplying by 3/4 every time. You could test it out if you want to. So multiply 3/4 times 3/2, you get 9/8. All right, now the pluses and the dots mean we're finding the infinite sum. So if we want, we could write this. Do I want to do that? Could write this in sigma notation. So we could say sigma notation n equals 1 to infinity, the first term times r to the n minus 1. Okay, so that's to generate the terms there. Anyway, that's going to equal this formula. So the first term is 2. Oh, I suppose we should look at, so this converges because the absolute value of 3/4 is less than 1. Okay, so what was I about to do? I was about to use that formula, but I've kind of crowded for space there, so I'm going to move that over. So the sum of the infinite terms is going to equal the first term over 1 minus r. Okay, so that's going to be 2/1/4, which again is a complex fraction, so I'm going to multiply by 4/4. So that's going to be 8. Okay. Pretty good. All right, so let's write this as a geometric series. So what we can do here, it's a little bit tricky. If we let the first term be 0.23, and then if we let the second term be this, and then 1, 2, 3, 4, okay, because that's a repeating decimal, so it's 2, 3, 2, 3, on and on and on. So that's what's happening there. So a sub 1 is going to be 0.23, and r, so if you take the second term divided by the term before it, first term, so if you take that divided by, I don't usually put zeros in front of the decimal, but it's fine either way. So that's going to be 1/100. Okay, if you move this decimal 1, 2, 3, 4, and you move this decimal 1, 2, 3, 4, 1/100. Okay, so we could write that in sigma notation. So that's going to be n equals 1 to infinity of 0.23 times 0.01 or 1/100. It's fine. Okay, so that converges. It's basically the same as the last problem now. Converges because the absolute value of 1/100 is less than 1. Okay, so the sum of the infinite terms is going to be 0.23, 1 minus 1/100. So that's going to be 23 over 100 and 99 over 100. So complex fraction, 23 over 99. All right, that's a good one. All right, so here we're just determining convergence. We're not actually going to find the sums. We're just testing to see do they converge or diverge. So here we're multiplying by 3/2 over and over and over again. So r equals 3/2. The absolute value of 3/2 is greater than 1, greater than or equal to 1. So diverges by geometric series. All right. So this one, we can rewrite that. So that's 3 times, and we could rewrite this as 1/2 to the n. If you think about it, if we move that over, it'd be 1 over 2 to the n, but 1 to the n. Hopefully you're okay with that. That's pretty straightforward. So the absolute value of that is less than 1. So converges by geometric series. Okay, over here we're going to split this one up. So we have n equals 0 to infinity of, so this would be 2, and then similar to the one over there, that would be 1/5 to the n. Okay, minus, and then we would have another one, and that would be 3/5 to the n. So here, the absolute value of 1/5 is less than 1, and here the absolute value of 3/5 is less than 1. So both of those are less than 1, so that converges by geometric series. Okay. So if we move down here, the negative exponent, we just flip that over, so that would be pi over e to the n. So r is equal to pi over e. So pi is 3.14159265358. Okay, you get the idea. And E is 2.71828. Andrew Jackson, 1828. Andrew Jackson served 2 terms. 1828 was one of the years of his presidency. And then it's a right isosceles triangle, 45, 90, 45. That's as far as I know that, but I know pi a little bit further than that maybe, but I haven't practiced that in a while. Anyway, the point is that r, or pi over e, the absolute value of pi over e is greater than or equal to 1, so it diverges by geometric series. Okay, and a lot of this chapter is stuff like this, except a little more complicated, talking about whether series converge or diverge. Okay, let's see here. So here, this is a little bit awkward. R is 1 plus k over n. All right. So if k is less than 0, then, okay, if k is less than 0, then this will be subtracting this, so that will be less than 1. If k is less than 0, then that equals that, and we have converges bigeometric series. If k is greater than 0, then it diverges. Alright, so here we're actually, looks like we're going to go back and find the sums of those. So I guess we could have just done that all at the same time. But so you want to find out your first term here, so that's going to be 0. So the formula says a sub 1, but it's the first term that you use. So anyway, a sub 0, 2 to the 0 power is going to be 1, so that's going to be 3. And then r is going to be 1/2. So we're going to have 3 over 1 minus 1/2, 3 over 1/2. So that's going to be 6. So we could say that that converges, the sum, that's a sum, converges to 6. I'm just going to write the answers down for the other ones instead of. Okay, so this one, if you recall, we divided that into 2. It's right there. So if we plug in 0, the first term is 2. So that's going to be 2 over 1 minus r. And then we're going to have minus, and if we plug 0 in there, our first term is 1. And r is 3/5. Okay, so that's going to be 2 over 4/5 minus 1 over 2/5. So this one I'm going to multiply by 5 over 5, and this one I'm going to multiply by 5 over 5 also. So that's going to be, I guess I could reduce here as well. So that's going to be 10 over 4, which is 5 over 2, minus, that's going to be 5 over 2 also. So that converges to 0. Okay. And here, the first term is going to be the first term that we're looking at. So don't get distracted by the number 1 or the number, whatever the number is, that's the first term that we're using. So if we plug a 1 in here, that's going to be negative 1/3, and r is negative 1/3. So that's going to be negative 1/3 over 1 minus negative 1/3. So negative 1/3 over 4/3. So complex fraction multiplied by 3 over 3, that's going to be negative 1/4. All right. And here, so the a sub 2, which is the first term that we're going to use, is negative 3/8. And r is, if you take that over, that's going to be 1/4. Okay. So, hold on a second. That's not 3/8, that's negative 3/16. 2, 4 squared, 4 times 2. Okay. 16. Alright, so that's going to be negative 3 over 16 over 1 minus 1/4. So negative 3 over 16, 3/4. Okay, so we're going to multiply that by 16 and 16. So that's going to give us negative 3 over 12, which is negative 1/4. All right. Okay. Now, properties of infinite series. So that and that. So if we have a constant, we can factor the constant out. We just have that. If we have a sum, we can separate them. We did that up there on one already if we have the difference. So that's pretty self-explanatory. All right, last page. Okay. So telescoping series. All right, so when we look at this, if we plug in 1 for these two ends here, we would get that. And then if we plug in 2, we would get this. And if we plug in 3, we would get this. We keep going all the way down to the last term before n, we get that, and then we would get that as our last term. Now what we want to notice here is that because there's subtraction between there, and what you have is a term minus the term before it, so this is going to cancel out, and this is going to cancel out, and this is going to cancel out with the one over there, and that's going to cancel out, and this is going to cancel out. So all that stuff in the middle is going to cancel. So that's just going to leave you with 1 minus 1 over n plus 1. That's going to be the sum. So what we want to do is take the limit as n approaches infinity of that. So that would be 1 minus 1 over infinity plus 1, which is infinity. So that's going to be 1 minus 0. So this converges to 1. Now those telescoping series, they can be a little bit more complicated than that in the middle. So they could be skipping some things, but you can still find that pattern where everything is going to end up canceling. Okay? All right. So let's try this one out. Now to do this, we're going to need to use partial fractions. So what we need to know is we have 1 over n times n plus 2. That's going to equal a over n. So this is a good review. I like how we bring stuff back that we did. So we're going to need to be able to break that up. All right. So if we multiply by n plus 2, we're going to get 1. We're going to have a times n plus 2 and b times n. All right. So if we let n equal 0, then this would be 1 equals 2a. So a would equal 1/2. And if we let n equal negative 2, then we're going to have 1 equals negative 2b, or b equals negative 1/2. All right. So if we rewrite that, both of those are going to have a half in them, so I could factor that half out. And we have n equals 1 to infinity. And so here, a was 1/2. We factored that out. That's just going to leave us with 1 over n. And here it was negative 1/2, so that's just going to be minus n plus 2. All right. So now, if we start to look at that, I'm going to bring that down here so I have more room. Okay, so let's start plugging some stuff in there. So we have the 1/2 out there. And then if we plug in 1, we're going to have 1 minus 1/3. Okay, that's our first term. And then if we plug in 2, we're going to have 1/2 minus 1/4. Okay, and then if we plug in 3, we're going to have 1/3 minus 1/5. And we'll do one more. If we plug in 4, we have 1/4 minus 1/6. Okay, now if we keep going all the way down here, then let's plug in n minus 1. So we'd have 1 over n minus 1. And then if we plug n minus 1 in here, that would be n plus 1. plus 1. And then our last one, when we plug in n, we get 1 over n and minus 1 over n plus 2. Okay, so this is a more complicated, like I told you, it'd be more complicated. So here, these 1/3 cancel out there, and then these 1/4 cancel out here, and then you can hopefully realize that that pattern would kind of continue there. So here, we're just going to be left with these first two things. And then down on the other end, I could have put one more term there. So should have put one more term in there. So right before this, we could have had, if we would have plugged in n minus 2, we'd have 1 over n minus 2 minus, and if we put n minus 2 in there, then we'd have 1 over n. So that one will go right there. So that's kind of showing that this is going to cancel here. And if we keep going back, then these will cancel as well. So we're going to end up with the last two off of this. Okay? So we're going to have the limit as n approaches infinity of, and I'm going to factor the 1/2 out in front of that limit. And so I'm going to have 1 plus 1/2 minus 1 over n plus 1 minus 1 over n plus 2. If you're a little bit lost here, it's probably not that big of a deal, but anyway. So that's going to be 1/2 times 1 plus 1/2 minus 1 over infinity minus 1 over infinity. Okay, so that's 1/2 times 3/2. So this converges to 3/4. Okay, we're almost done. All right. We want to start memorizing the names of these different tests. So first, one of the ones, we can use the geometric series, but here we want to use the nth term test. The nth term test. So actually just this part, I should have just highlighted that. Okay, so if the limit of the term, the value of the term does not equal 0, then the sum is going to diverge. So that should make sense if you just think about it. If we're going to keep adding a number on, if that number is not getting closer to 0, then it's going to diverge because you keep adding more and more and more and more. The concept on the geometric sequences where r was less than, the absolute value of r was less than 1, is that we keep multiplying by this number between 0 and 1, the absolute value, and that's going to make the amount we're adding smaller and smaller. So the amount we're adding is getting closer and closer to 0. So if we're getting really close to adding 0, then we're not changing the sum anymore. And so what we can do here is we can test to see what that last term looks like. Okay? Now, the converse is not true. So just if we switch the order around, if we say that this diverges, then this can't be 0. That's not true. So it doesn't work in that direction. Okay. So what we want to do here is take the limit of that as n approaches infinity. So we're looking at the limit as n approaches infinity of this. So what we can do there is focus, from pre-calculus we would focus on this here, and hopefully that's pretty clear. We also could divide all of these by n cubed. So this would be 1, and this would be 2, and this would be 4 over n. I guess we could do it that way. So if we divide all those by n cubed, we would have 4 over n minus 1 over 10 over n cubed plus 2. Okay? So that means those are both going to go to 0, so that's going to be negative 1/2. Negative 1/2 does not equal 0, so this diverges by the nth term test. So some of the questions on the AP exam are multiple choice, and it'll say like which test or whatever. So you're going to have to be able to figure that out. So that's why you need to memorize these tests as we go. Make sure you know this test. This one's pretty easy, so you want to make sure the more of them you know, the easier it'll be to answer those on multiple choice tests. So part of it will just be eliminating some. Like you'll know, okay, I know the nth term test, and that's not the nth term test, so I can cross that one off. And being able to cross some of them off is really going to help you. Okay, so now we want to find the limit as n approaches infinity of this. Okay, so that's going to be infinity over infinity. So what we want to do here is take the derivative, use L'Hopital. So we're going to take the derivative of both of those. The derivative of e to the n is e to the n. The derivative of n is just 1. So we have e to the n, and we can plug infinity in there, and that's infinity. So infinity does not equal 0, pretty much the opposite. So the diverges by the nth term test. Okay. All right. Now, we're going to take the limit as n approaches infinity of all of this. What we can do here is focus on these. So that would be negative 5/7, actually negative 5 over 7n. So as that approaches infinity, that's going to be negative 5 over infinity, which is 0. Okay, so this is what we were just talking about. The converse is not true, so we can't say anything about, so it's inconclusive. So we tried to use the nth term test. I don't even know if we would say the nth term test. We'd probably just say it's inconclusive. We don't know. Because this is just if it doesn't equal 0. If it does equal 0, we don't have enough information. All right, it's about that time. Be good. Have a good day. Just real quick, I don't know if you noticed the shirt or not, but the students made that a long time ago. I can't remember what year that was. They had like a concert shirt. They had all the dates of the AP exams. So let's go. We can do this. All right. Be good.